Hi everyone, welcome to the new video. In today's video, we are going to talk about the symmetric relation. So this session is going to be the extended session of the previous session. Okay, so let's start with it. Symmetric relation. Okay, so let's take a set A. Here I have set A, and in this set I have three elements, 1, 2, and 3. And again here I have set A with the same elements 1, 2, and 3. Okay, and now R is a relation defined from set A to set A, or R is the relation on set A. Okay, and the relation is defined in the way that 1 is related to 2 and 2 is also related to 1. Okay, so this given relation is R 1, 2, and ordered pair to 1. Okay, this is symmetric relation. Why? Because a relation is said to be a symmetric relation if A is related to B, then B must be related to A. Here, A is related to B, then B must be related to A. I hope you understand it. Okay, so in other words, I can say that in mathematical language, I can say that a given relation R is said to be the symmetric relation AB and BA, right? For all A related to B, we have B related to A, right? Where A belongs to your set A, and B belongs to set B. Okay, so this is how you can define this symmetric relation, or you can also write here it's going to be AB and here BA, right? Such that AB belongs to R, right? BA belongs to R, and A belongs to A, and B belongs to B. Okay, so it's the same thing. Means that a relation is said to be the symmetric relation if AB is in the relation, then BA must be in the relation too. Okay, so if A is related to B and B is not related to A, then it is not going to be the symmetric relation. I hope you understand it. Okay, so this is very important here. I'm writing here. So here, if A is related to B, then B must be related to A. Okay, so if this condition is valid, then the given relation is said to be the symmetric relation. Okay, you can look at some questions. Okay, for example, let's say that here we have some relations R1, R2, R3, R4, R5. Okay, so relation R1, it is 1, 1. Okay, relation R2, it is just empty set. Then relation 3, here I have 1, 2, and here 3, 1. Relation 4, 1, 2, 2, 1, right? And here 2, 2, 2, 2. And here relation 5, I have 1, 1, 2, 2, and 3, 3. Okay, so we have to find what relation is symmetric and what relations are not symmetric. Okay, let's start with R1. R1, okay, relation 1, 1, 1, ordered pair 1, 1. What do you think? Is it symmetric? Yes or no? This relation is symmetric. Yes. Why? Because if you look at this relation, A is related to B. If this is A, this is B, then B is also related to A. Okay, if you say this is A and this is B, then for all A related to B, we have B related to A. Means that if one is related to one, then one is also related to one, which it says. So yes, this is going to be the symmetric relation. Next is R2 empty set. Okay, so what do you think about this? Yes, it is going to be, yes, it is going to be symmetric relation. Now you will say, how? Now tell me, A is related to B, okay, and A relation B gives you this null set, right? Okay, A relation B, it just gives you empty set. So B relation A also gives you the empty set. So which means that your empty set is always going to be the symmetric relation, or your empty set, it is always it always follows the condition of the symmetric relation. So R2 is symmetric. Okay, now come to R3. R3 relation 3, we have two ordered pairs 1, 2, 3, 1. Now see here, if you take here this one as A, this one as B, then if A is related to B, we must have B related to A. So 2, 1 is missing here. Same, if 3 is related to 1, then 1 must also be related to 3. So this is not a symmetric relation. Next, what about this? Now see here, this is A, this is B. If A is related to B, we have 2, 1. So fine. And here we have AB, 2, 2. So if 2 is related to 2, then it is again the symmetric relation. Why? Because 2, 2, both the elements are same. If 2 is related to 2, it means that 2 is related to 2. It follows the condition of symmetric relation. Then R5, yes, this is also the symmetric relation. Now because A and B are same, A related to B, B must also be related to A. A again same. If A is related to B, B must be related to A. B and A are both same. If A is related to B, then B must also be related to A. So this is symmetric relation, which says that if A is related to B, then you must have B related to A. Understand? I hope you have clarity on symmetric relation. Okay, now let's go to the next one. Okay, there is one more thing. How many symmetric relations? Number of symmetric relations. Okay, number of symmetric relations that can be there on the given set, or how many symmetric relations can you make? Okay, so just write it down. Number of symmetric relations, number of symmetric relations, possible symmetric relations, possible on set A. Okay, so let's say that I'm just talking in the general context. Okay, let's say that my I have a set A, and this set A, it has n terms, okay, up to a n, right? So because I have to find out how many possible symmetric relations can I make on, or can I have on set A, or from set A to set A. According to the definition of relation, we know that relation, it is subset of the Cartesian product of two sets. So if it has to, because symmetric relation, it is defined on the same set A, right? From set A to set A. So here, if I take the Cartesian product of A, or I would say a Cartesian product A, then it will look something like this. So here it will be A1, A1, right? A2, A2, AN, AN, right? Then we have terms like here A1, A2, then A2, A1, then so on up to A n minus 1 up to AN, and then an minus 1, right? Now I have to develop the possible symmetric relations from this Cartesian product. Okay, so let's say that here R is the symmetric relation. Okay, R is the symmetric relation on set A. Okay, then what would happen? Then what are going to be the possibilities? Okay, now let's see that. Now, the symmetric relation definition says that if A is related to B, then B must also be related to A. Okay, so if this element has to come here, it has two possibilities. Now, what could happen? It can say that, yes, I can go and join this relation, fine, or the second chance is that, no, I do not want to be a part of this relation. If that thing will happen, then here it's going to be the empty set, which is again the symmetric relation. So I hope you understand what I'm trying to say. Means that this element has two possibilities. Okay, so same goes for these n elements. You will have two possibilities. Okay, so here A1, A1, so on up to AN, AN. Okay, so how many possibilities do you have? For these n elements, you have two possibilities, which means that from here to here, I have 2 raised to power, or 2 raised to power exponent n possibilities. Why? Because either they can be a part of this symmetric relation, or they prefer to stay out. Okay, if they prefer to stay out, it's going to be the empty relation, which again is the symmetric relation. Okay, and then here for these thing, okay, now see here, I have n terms and n elements, right? Now, sorry, I forget to tell you here, A, it represents the set of n elements. So here, n of A, number of elements in A, it's going to be n. And when I took n, a Cartesian product A, then here the total elements would be, now see here, n of A cross A would be A multiplied by n of A, which is n square. So total number of elements here would be n square. So n came here. So what is left? From here to here, I have n square minus n. I hope you understand it. Right? Now, for these elements to join this reflex symmetric relation, now they have to come in the pairs. Now, A1 and A2, for example, this ordered pair cannot come alone, right? Why? Because if A is related to B, then B must also be related to A. Then they have to come in the pairs here. Okay, so for all these left terms, n square minus n, how many pairs are possible? So how many pairs are possible? It would be n square minus n divided by 2 pairs. Pairs are possible for these terms left here, right? And again, these will have a possibilities. Now they will come in the pair. They can choose to join this, or they can also choose to stay out of it. So again, two possibilities are there. Okay, so if two possibilities are there, then it's going to be 2 raised to the exponent n square minus n divided by 2, right? I hope you agree with me. Okay, so we have same base. Then what happen when we have same base? Then powers get added up. So here it would be 2 raised to power n plus n square minus n by 2, which is equal to 2 raised to power uh, n square plus n by 2. Okay, so total possible relations, total possible symmetric relations, symmetric relations on set A with n elements is equal to 2 raised to power n square plus n by 2. Okay, so please note it down. This is very, very important result. Okay, so here, let's say that if you have a set which says that, oh, it's not working. Let's say that you have a set A equals 1, 2, 3. Okay, so this is the set A with 3 elements in it. So how many possible symmetric relations you can make on this set? It would be 2 raised to power, how many elements? 3. 3 square plus 3 by 2, which is equal to 2 raised to power 9 plus 3 by 2, which is 2 raised to power 6. Okay, let's say that here you have just 2 elements here, 1, 2. Then how many total symmetric relations are possible? Okay, so it could be, let's say R1, it could be first the empty, right? Then R2, it could be your 1, 1, 1, 1, and 1, 1, and 2, 2, right? Or it could be R3, it could be 1, 1, 2, 2, and 1, 2, 1, 2, and 2, 1, right? R4, what it could be? R4 could be, it could be 1, 2, 2, 1, right? And R5 could be 1, 1, 1 2 2 1, right? R6 uh, could be 1 2 2 1 again, 2 2 2 2 1 2 2 1. R7 could be 1 1 2 2 1 1 2 2. How many possible relations? 2 raised to power n square, 4 plus 2 by 2, 2 raised to power 3 8. So R7 could be, this is done, 1 2 2 1 1 2 2 1. All right, then this 1 2 came with 1 1, then 2 2, then then 2 2, right? Then what is left? 1 1 2 2, 1 1 1 1 2 2, 1 1 2 2 is done. This is done. 1 2, yes. 1 1 2 2 1 2, no, that cannot be done. So 1 2 2 2 1 1, yes. This is okay, this is okay too. 1 2 2 1, fine. Oh yes, 1 is going to be just 1 1 1 1, and R8 it's going to be 2 2, right? So you can see 8 relations. Why? Because here I have taken both. So what about if you just take only one? So again, then it's going to be, because see here, 1 1, if A is related to B, then B must also be related to it. So it follows this. So total 8. So you can say that the total possible symmetric relations would be 2 raised to the exponent n square plus n by 2, okay, which you can clearly see here. Okay, so I hope this thing is clear to you. Okay, now let's switch to the next one. Next is your transitive relation. Okay, transitive relation. Now, what is transitive relation? Transitive relation is very important, and it is one of the relation that is most confusing to the students. Okay, students find it most confusing, but it is very simple. You just have to know how to interpret it. Okay, so we are going to talk about it. So the next is transitive. Okay, this is a transitive relation. Okay, so what is transitive relation? Okay, now a given relation, okay, we'll start with the definition. The definition says that a given relation is said to be a transitive relation if A is related to B and B is related to C, then A must be related to C. Okay, so here I'm just going to mention few things. Okay, so let's say that here I have set A, and here again set A. Okay, so here I have relation from set A to A. So here I can say that relation is on set A. Here I have elements 1, 2, 3. Again, same elements 1, 2, 3. Okay, now see here what it says. It says that if A is related to, B, right, and B is related to C, okay, means that if 1 is related to 2 and 3 is related to 1, okay, then 1 must be related to 3. 1 must be related to 3. This is what it says. If 1 is related to 2, if 1 is related to 2, no, this I made it wrong, right? If 1 is related to 2, 3 is related to 1. If 1 is, if 1 is related to, see here, I've made some mistake here, I guess. Okay, this is set A, 1, 2, 3. Set A, 1, 2, 3. Okay, so here it says that if 1 is related to 3, right, and 3 is related to 1, then 1 must be related to 1. Then 1 must be related to 1. Okay, so this is what it says. Okay, so here R is a relation on set A, so R is said to be, now R is said to be, okay, relation R is said to be transitive if A is related to B and B is related to C, then A must be related to C. Okay, or in other words, I can say that R, it is said to be transitive, right? It is said to be transitive. AB, BC, AC, for all A, B belongs to R and BC belongs to R, you must have A, C belongs to R. So this is the definition of here transitive relation. Okay, now one thing is very important here, which is this: if A is related to B and B is related to C. Okay, now this thing will happen only when this and this is possible. Okay, try to understand what I'm trying to say. Okay, A must only be related to C if A is related to B and B is related to C. If only A is related to B and B is not related to C, or B relation C is not given to you, then it is still transitive. Understand what I'm trying to say? See here, what I'm trying to say here is, let's say that here I have a relation. Okay, this is R1, right? And the relation says that uh, it is 1, 3. Okay, and they are asking you if this relation is transitive or if this relation is transitive or not. So this relation is transitive because here, if you think of this as A and this as B, then A is related to B. A is related to B, that is fine. Now, B is related to C, that is not given, that does not exist here. So it doesn't affect the nature of this relation. It is going to be transitive, but if it says that R2, it is 1, 3, and this is 3, 2, then here you have or just these two things. Now see here. Now here you have two elements, right, in this relation. Now you look at this relation, it says that A is related to B, okay, and B is related to C. Now here, A must be related to C, so this is not a transitive relation. Why? Because here AB is given, BC is given, so you have A relation C must be here, right? Let's say there is one more relation, R3, which says 3 here, 3, 2 here, 1, 2. Now see here, this relation is transitive. Why? Because here A is related to B, B is related to C, and A is also related to C. So this thing, remember, a given relation is said to be transitive if A is related to B and B related to C, only then this thing is going to be possible. But if you are just given with A relation B and you are not given with these two things, then again, your relation is said to be transitive, because this possibility is only when you are given with these two things. But if only one thing is given, then still your relation is transitive. I hope you understand my point. Okay, let's say that you are given with a set. We'll try to do some questions on it. Okay, let's say that you are given with a set of these three elements, 1, 2, 3, 1, 2, 3. Okay, now here you have given relations R1, which is your 1, 2, then R2, you have 1, 2, 2, 1, here 1, 1. Then here R3, you have 1, 2, 2, 3. Okay, R4, 1, 2, 3, 2. R5, empty relation. R6, 1, 2, 2, 3, 3, 1, 2, 2. R7, 1, 2, 2, 3, 3, 2, 1, 3. Okay, you have to find out what relations are transitive and what are not. Okay, let's start with number one. This is the given this is the given set. Okay, so this is the given set, and R is the relation defined on this set A. So these all relations are defined on this set A. Now let's start with R1. R1 says R1 contains one ordered pair, and which is 1, 2. Now see here, 1, 2 means that this is A, this is B. A is related to B, but you are not given with B relation C and A relation C. So it's fine. There is no problem with it, because this thing is only possible when these two things are already given to you, right? But only one thing is given to you, which is 1, 2. So this is going to be transitive. It won't affect the nature. So it is going to be transitive. I hope you understand it, because A is related to B, it's fine. If B is related to some C, then A must be related to that C, right? But B relation with C is not defined here. Here we are only given with A is related to B or A relation B. So this thing is going to be transitive. I hope you understand my point. Go to the next relation to, this is 1 2, fine, A B. Okay, now see here, this is AB, right? This is BA, right? So A is leading us to B, B is leading us to A, then A must lead us to A. So which is this, means that this relation is also transitive, right? Now A, B, and C, they should not be the same all the time. They should not be the different all the times. They can be the same, right? So not necessarily they must be the distinct. Understand? So see here, what I'm trying to say here is that here B and C are, sorry, here B A, B, and here B, C. So you can see that A and C are same here. So again, it is valid. Okay. Then here 1, 2, 2, 3. Okay. Interesting. Now this is A, B, right? This is B. This is C. Now A, B is given, B, C is given. Then what about A relation C? That is not given, which means that it is not transitive. Why? Because here you are given with both of these, but this thing is not mentioned. If one is given to you and others are not mentioned, it's fine. But if both are given to you, both these things are given to you, then it must be there, right? Now go to this 1 2 3 2. Now see here 1 2, if this is A, this is B, okay, then this is B, but this is let's say this is C, okay. So A is related to B, but B is not related to C. Then I would say that this is not your transitive relation, okay. Then next, this empty relation, yes, it is your it is your transitive, right? Why it is transitive? Because A is not related to C, B is not related to C, A is also not related to C. Understand? Next, R6, this is 1 2. Let's say this is AB, then this is BC, then 1 must be related to 3, but here 3 is related to 1. So again, this is not, right? So this is not here a reflexive relation. Go to the next. This is 1 2 AB. This is BC. Then 1 3, 1 3 is here. Wow, that's a good thing. Okay, but if you look at one more thing, this is fine. Okay, this and this resulted in this, it is fine. But what about this? Now look at 2 3 and 3 2, A B, okay, and this is B C. Then what about 2 2? So this is not. Why? Because 2 2 is not in your relation. I hope this thing is clear to you. Okay, and here 2 2 is not in the relation. If 2 2 is here, then it's going to be a transitive. So always remember, your relation is going to be transitive. If A is related to B and B is related to C, then A must be related to C. But if if only A is related to B and relation of B with C is not given, then it's fine. There is no problem. If A is related to B and relation of B with C is not given, it is fine. If B is related to C and relation of A with B is not given, it is fine too. Then again, it's the same thing. Okay. So I hope you understand this whole concept of transitive relation. Okay. Now let's switch to the next one. And the next one is equivalence relation. Okay. So equivalence relation. Equivalence relation, it is nothing. Your relation is going to be equivalence relation if it is reflexive, symmetric, and transitive. That's it. Okay. So what does it mean? Equivalence relation. Okay, so here I will say that R is said to be equivalence relation if it is reflexive, symmetric, and transitive. Okay, so how is it possible? Let's say that we have here A, here A, again the same elements 1, 2, 3, here 1, 2, 3. Okay, and here 1, here this is a relation, right? And here 1 is related to 1, 2 is related to 2, 3 is related to 3, and here 1 is also related to 2, and here 2 is also related to 1. Okay, now let's see that what will we get. So here R, it's going to be 1, 1, 2, 2, 3, 3, 1, 2, and 2, 1, right? Now, let's see that if it is reflexive, reflexive says that a relation is said to be reflexive if all the elements of A are related to itself. So 1, 1, 2, 2, 3, 3. So these three pairs, ordered pairs, make this relation reflexive. Okay. Then symmetric, if A is related to B, then B must be related to A. Yes, this is symmetric, 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 right? Then transitive, which says that if A is related to B and B is related to C, then A must be related to C. So this is transitive. Yes, this is transitive. Yes, this is transitive. Yes, this is transitive. 1 is related to 2, 2 is related to 1, then 1 must be related to 1, where and it satisfies that. So here I would say that R is equivalence relation. Equivalence relation. Okay, I hope you understand it. So any relation which is reflexive, symmetric, and transitive is equivalence relation. Okay, now one more thing here. Number of your reflexive and symmetric relations on possible, okay, possible numbers of possible numbers of reflexive and symmetric relation. Okay, so total possible numbers of reflexive and symmetric relations on set A. Okay, so let's say that again, we assume that this is set A and it has n elements, A2, so on up to AN. Okay, and here I know that number of elements, here it is n. So if I do the Cartesian product of this set, then it's going to be A1, A1 to AN, right? And here I would get something like A1, A2, A2, A1, then here AN minus 1 to AN, and here AN to AN minus 1, right? Okay. Now, let's say that this R is the relation, and this relation has to be reflexive and symmetric. So we have to find that how many possible such kind of relations are possible on this set A. Okay, now see here. The main condition for reflexive is that, now one thing here, the total elements here is going to be n square, right? I hope you know it because number of elements in this set is n. So A cross A n square, right? And from here to here, you have n, and so the left one here would be n square minus n, right? So to make this relation reflexive, then these elements have to come here, right? So what would happen? This one, A1, A1, so on up to AN, AN. Okay, so this is the minimum condition. It has to stay here. But now, see here, what would happen? So if this relation has to be symmetric, right? If this relation has to be symmetric, then what now? Then these elements have to come here and they have to come in the pairs, because symmetric relation says that, if A is related to B, then B must be related to A. So if this relation has to be symmetric as well as reflexive, then these pairs will decide the nature, right? And if they will come, so these are n square minus n terms, right? And if they have to come in pairs here, right? A1, A2, A2, A1, so on up to AN minus 1, AN minus 1. Okay, now they have two options, right? They have two options. Either they can come here. If they come here, then this relation is going to be symmetric. If they prefer to opt out, then again this relation is going to be symmetric. So the total possible number of combinations that we can have, okay, for each pair we have two possibilities. So for n square minus n by 2, why by 2? Because these terms will come in pairs. So how many possibilities are we going to get? We are going to get 2. We are going to get 2 raised to the exponent n square minus n by 2 possibilities. Okay, I hope you understand it. So from here, I can say that the possible number of reflexive and symmetric relations on a given set, it's going to be it's going to be 2 raised to the exponent n square, 2 raised to the exponent n square minus n divided by 2. Okay, so I hope you understand it. You can apply this formula anywhere. It will work out like what we did before. Okay, so I hope the derivation, how we have gotten this formula, it is clear to you. Okay, so this marks the end of your types of relation. In next session we are going to take few questions, and we will try to have more clarity on the relations. Okay, so have a great time, and we'll see you next time. Bye bye.